All right. Welcome everybody to today's seminar. It's a pleasure to introduce Sarwar Ahmed from Wuppertal, visiting us from Wuppertal this term. He's a PhD candidate there, working with Radim Dardashti and someone else.
Tanya Ackerman, she's a historian.
Yeah. Anyway, it's great to have you in Oxford with us this term. Over to you.
Thank you very much for having me here. Special thanks to James, Oliver, and also Sam that made it possible that I present part of my work here. So today I kind of present an epistemological problem in the scientific observations that I call inference to the source. And I illustrate that with a case study, which is like observing the binary black hole measure. So as an outline, the whole talk will be revolving around these points. I will argue that concerns about circularity, concerns about circularity regarding inference to the source to be observed are actually consequences of the hypothetical deductive method. And the epistemic problem or threat is under determination of the source by information rather than circularity and theory ladenness. I'll talk about this. People have reasons like concerns about circularity and theory ladenness. And I propose a bidirectional inference to the source, to the only explanation that account for the inference to the source. However, I argue that to provide a full epistemic justification for the observation, a broader concept of evidence is needed to overcome the underdetermination. And I will argue that this needs the kind of integration of meta-empirical assessments to infer the inference to only explanation. So the talk is divided into three parts. In part one, I will just kind of give you a background about what do I mean by inference to the source. And I also reassess the methodologies that are provided for inference to the source. Especially, I'll talk about HD method, eliminative reasoning, and inference-based explanation. And then I will present the case study, which is observing a binary black hole merger. I talk about the epistemic challenges, the circularity concern, and I also kind of touch upon parameterized post-Einsteinian framework and somehow its limitations. And then I will come back to the philosophical aspect. I argue for an inference to only explanation. I talk about the interdetermination, meta-empirical assessments. So what do I mean by inference to the source? So suppose that we have a theory T, that the theory predicts X, and then suppose further that the entity, the X is a kind of entity or a phenomenon that is imperceptible to our naked eye, but we can kind of observe it with instruments. And then in this case, normally scientists kind of collect a presentational data through kind of experimental or instrumental setup, that this representational data is supposed to represent X, which is a phenomenon in the external world. So a crucial inferential step, I think, is in this kind of scientific observation. How do we infer X that is observed? In other words, we need to provide a reliable causal explanation between the data, the representational data, and the source, which is X. You can also think about it in terms of like cause and effect. So one should not actually conflate the theory of X and X. By X, I mean, or the source, I mean the natural phenomena in the external world, and the theory is our expected theoretical description of it. And the issue here is, well, what is the reliable methodology to infer this natural phenomenon, given that we have a detected representational data and our expected theoretical description? So many people have talked about it, but I'll just give you a very short illustration of different methods. I'm sure that all of you know about this. If we talk about hypothetical deductivism, one normally starts with the hypotheses and then by finding consistent observations for its deduced predictions and with a kind of confirmed hypothesis. But when it comes to eliminative reasoning and inference-based explanation, it's the other way around. When it starts with evidence, goes through a process of elimination based on evidence. Evidence can be theoretical and empirical evidence, and then by elimination, comes up with an explanation. So the direction of ER and IBE is from evidence to hypothesis, but the direction of hypothetical deductivism is from hypothesis to evidence. So now the question is, well, the received version of these methodologies, whether they can account for this inference or not. If we start with hypothetical deductivism, well, it's very well known that to truly test a theory according to this reasoning, the theory should not be involved in the observational process. So according to the reasoning, this kind of theory readiness may lead to even circularities. And I think by the same token, philosophers have opted for a kind of normative argument for the theory of the source. And they argued that the theory of the source should not be involved in the observational process. Examples are Ian Hacking, Peter Koso, Jody Azuni. And more relaxedly, Alan Franklin has argued that an independent test of the theory of the source is required if it's allowed to be involved in the observational process. So more concretely, Hacking argues that something counts as observing rather than inferring when the bundle of theories upon which it relies is not intertwined with the facts about the subject matter under investigation. Here he refers to Dudley Shapir's very well-known article, The Concept of Observation in Science and Philosophy, where he criticizes Shapir, although he says it's the best account of observation, but he criticized Shapir based on that. And then we have Peter Koso. He argues that inferring the source of information X is reliable only when it is reached through a theory independent of the theory of the source of phenomena. When it comes to the reality of theoretical entities, like something like electron, Jody Azuni has argued that like perceptual observations, robust instrumental interactions are independent of the theory of the object. So I think John Worrell has nicely illustrated that in general. He has argued that hypothetical deductive reasoning requires an independent test of a theory that postulates a cause to explain a phenomenon in order to show that the cause is indeed behind the phenomenon. I think there are counterexamples. One example is what I will be presenting here. And a more fundamental problem is an determination problem. I believe that many modern scientific observations are observations of so-called theoretical entities that are predicted by a particular theory or models of the theory. And the properties of these entities or events are represented by the theory that predicts them, right? So even in cases where this argument from independence holds, one has to give reasons why we should believe that the data really corresponds to the target system described by the theory or a model, not something else. More importantly, different theories or models may predict inconsistent target systems, or even the signal might come from something which is not conceived. Yeah? So the upshot for this section is that the philosophical accounts of inference to the source are either too flexible, rendering them epistemically insignificant, like Shapir's account, which I haven't touched upon actually, but yeah, you may know about it, or too normative, preventing them accurately reflecting scientific practice. Or more fundamental problem might be these accounts have employed HD method, and this HD method doesn't align well with the inference to source in observational processes. Then here I shift the discussion into the relation between data and phenomenon. And the very well-known paper by Bogan and Woodward, in there they kind of distinguish or identify two senses of IBE, inference to best explanation. They say H is the best explanation for E because given the other alternative causal explanations competing with H is the correct one. Or H is the best explanation for E given the other alternative causal explanations that compete with H has the best explanatory power. And they further argue that, well, the explanatory link between data and phenomenon is the first version, which I think it's better to be called inference to only explanation because it's based on truth conditions. And it's also obvious that it's a species of eliminative reasoning rather than inference to best explanation. Well, and then based on Bogan and Woodward, Michaela Massimi has built on their paper, and she has introduced data models, theoretical models, and background theory in the process of inferring the predicted phenomenon or entity. So for her, data models provide the observed phenomenon and manifest the value of the phenomenon. The theoretical models compete to explain the observed phenomenon by incorporating properties of theoretical entities. So for her, observed phenomena is actually the signal or the data, because she is still in the camp of the empiricists that the concept of observation for her is not extended beyond the naked eye. And then we have the background theory contains a family of models imposing constraints on the possible expected value for the parameter that the data model measures. So to some extent, the background theory helps to provide information in the inference process. So if I present with a kind of schematical representation, it would be something like that. So from bottom up, we have the background theory, and then the background theory provides theoretical models from top down, and then from bottom up we have the experimental result, and from the experimental result we have data models, and then by this bidirectional inference, the best fit model is selected. However, this is a two-step reasoning. First, one needs to delimit the space of alternatives, and then systematically and bidirectionally eliminate all but one alternative based on the evidence. Again, so the evidence could be like theoretical and empirical evidence. And there is a whole literature about that. Probably the best representation is from John Norton. He has argued that the first step is based on those assumptions, arguments that are general enough and uncontroversial enough to encompass a large number of alternatives. So Norton has used this methodology to many things like GR, black body radiation, Newtonian gravity. And Michaela has argued that it is the first step is based on theoretical constraint or pre-existing independent theory with a broader scope of application. So the conclusion, I think, of this IOE, inference to only explanation, is only adequate if both steps are justified. So where does the justification for the first step come from? I'll come back to that. Now I'm presenting the case study.
So can I just ask, what is the Norton article, 95?
I think it is something about the discovery of electron. Something like that. He talks about this methodology in several papers, actually.
Thank you.
Many of them are in the 90s. Yeah, he has another article talking about overdetermination, I think. It would be there as well. So on the 11th of February 2016, the LIGO Scientific Collaboration and Virgo published a paper in which they reported that in September 14, 2015, the two detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, simultaneously observed a transit gravitational wave signal. So in the discovery paper based on that, they have argued this is the first direct detection of gravitational waves and the first observation of binary black hole measure. And here I'm mostly concerned with the latter. I take gravitational waves as just information carriers. So because this is two observations, one of the gravitational waves and the other is the binary black hole. And more specifically, I am concerned with this first announcement of the observation of binary black hole measures as an accepted observational claim in a specific period of time. So this event, because after that, there's other observations of neutron stars and black holes, but this was the first one. So yeah, as I said, I take gravitational waves as information carrier. The information is encoded in the wave characteristics, such as the amplitude, the frequency, and the time of arrival. And as you all know, the observation is based on a theoretical prediction, which is specifically Einstein's general theory of relativity. And what is important here is that the Einstein's field equations do not provide exact solutions for compact binaries, like exact analytic solutions. So to go about this problem, the scientists have used approximations or models to predict the gravitational waves that compact binaries may produce. This is a very complicated process of modeling, but this is a very simplified version of it. As you see from the picture, the merging process is divided into three phases: the inspiraling phase, merger phase, and ring down, and different models are used for these different phases of the merger. You have the post-Newtonian approximations, mostly for the inspiral phase, but then they break down when the separation decreases and the velocity approaches the speed of light. And then we have the numerical relativity, mostly simulations designed for binary black holes. It's claimed that they are very accurate in the case of merger, like the ring down, but they are actually, the application is constrained by technologies and technological, computational, and scientific limitations. And we have other models, but mixed models as well, that we don't need to go into details. The detection process doesn't concern me very much, actually, but I will just mention it that two techniques are used to detect gravitational wave signals. One is matched filtering. It's a model-based search. Basically, it's looking for a match between defined gravitational wave templates, like the waveforms, and the unknown signal which is detected. We have the unmodeled search. This is a kind of, you have two detectors. You search for simultaneous patterns of data. That's why it's called unmodeled. But what is important here is that the second one, which is unmodeled, is not enough. You need the first one, which is the modeled one, and it's essential. So the second one is not enough. It's not sensitive enough to infer the source. Without the waveform models, the observation wouldn't be possible, as the source cannot be inferred from the data. So a number of scientists and also philosophers have arisen epistemic concerns. One is from Cutler and Wallis-Neri. They raise generally, this is a general epistemic concern about observing compact binaries. And it's due to the assumptions and simplifications behind these models or within the models, in the model construction. And we have Yunus and Pretorius. These two guys have played a central role in developing these models, especially numerical relativities. In a very well-known paper, they argue, or they distinguish two sources of error: modeling bias and fundamental bias. By bias, they don't mean bias in the philosophy of science. It's a epistemic uncertainty. The former concerns the inaccuracy of the models with respect to GR, and the latter concerns the inaccuracy of GR with respect to the source system. There is a nice paper by Lydia Patton, she argues that, well, if a model assumes that a phenomenon has a certain property, there is no guarantee that deviations from this assumption can be detected during testing. And there is another paper by Jamie Elder. She has in detail argued that there is a circularity in this observation, namely the accuracy of the models must be established using the LIGO-Virgo observations, but these observations assume the accuracy of these models. So this is about model inaccuracy. So in a nutshell, the problem is the binary compact objects are inaccessible in terms of like manipulation and intervention, if you think in terms of ion hacking. So we cannot calibrate the interferometry against them. And second, there is no alternative channel to get access to them. And thirdly, the phenomenon represents a regime that has not yet been tested, so the previous success of GR doesn't guarantee that it will be correct in this regime as well. In our terminology, the theory of the source is involved in the observational process, and there is no independent empirical support. Yeah, so there is an interesting framework which is called parameterized post-Einsteinian framework. I'll just mention it very briefly. It's developed by Yunus and Pretorius. It's from 2009 actually, and it's developed for the kind of excluding alternatives after the detection. But since it was developed before the observation and philosophers have talked about it, also mention it. I think it's a kind of counterfactual strategy in which the variables and assumptions of the theory are parameterized to track their sustainable range. And this results in like kind of generating counterfactual waveforms or theoretical models whose predictions may differ from the fundamental theory, in our case, GR. One can already find similarities between this strategy and Norton and Massim. However, the PPE framework is only developed to identify deviations from GR for the binary black hole measures, and also the viable proposed binary compacts, such as boson stars that mimic black holes. And the framework cannot actually provide an exhaustive number of possible models, nor is it a framework capable of identifying an exhaustive list of deviations from GR to exclude all alternatives. And now the question is, well, why one is justified in not exploring the full space of possible binary compacts or any other unknown entity that might mimic black holes in emitting gravitational waves, and why one is justified in not exploring the full space of gravitational theories that might in turn represent different sources of gravitational waves. So within the canonical understanding of the concept of observation so far, the source of the gravitational waves is inherently indeterminate by the gathered information. So yeah, now I go back to the philosophy side of it. Well, if you go back to the HD method, I think it might be clear now that this alleged circularity by Elder in the case of binary black hole observation falls into the same category of hacking and so on the others. So the involvement of the theory in the observational process. But to see this situation as circular, I think it's to interpret the process of observation within the framework of HD. And as we have seen, the epistemic problem arises from the indetermination of the source by information other than theory datedness or circularity. To illustrate this more, let me put it like that. Yep. So in the paper, Lydia Patton has distinguished two sets of parameters in the LIGO methodology. The first step is called hypothetical physical parameters that are constructed, used to construct the numerical relativity models, and then we have the estimated physical parameters that are inferred from the detection waveform. And as you see from the diagram, we have the background theory. Well, this is my representation. She doesn't do something like that. We have the background theory from the top down, and we have the strain data from bottom up. And then from the background theory, we have physical parameters like ship mass plays a central role. And then we have theoretical models. And then we have the estimated physical parameters that are inferred based on the detected waveform. And then there's a search process finding the best fitting waveform template. So the source manifests itself in from the data model resulting from a reliable detector, and from the theoretical models constrained by theoretical background and principles. Eventually, there is a kind of convergence towards selecting the most appropriate candidate. So the observation of the binary black hole measure involves bidirectional inference, similar to Makela-Massimi, but as I said, like Massimi doesn't kind of extend the concept of observation to theoretical entities. That's why the paper is called Saving Unobservable Phenomena. So to illustrate it more, we have an upward path. We have the data reveals a frequency signal evolution that indicates there is a kind of in spiral merger ring down of the compact bodies, and we have the downward path that the theoretical models introduce various binary compact entities, and then through kind of an elimination, the most fitting model is selected. Or you can call it saving one theoretical entity. And to support that, I have two quotations from the discovery paper, which I think supports my claim. So the first one is talking about, well, what is the evolution? What's this evolution represents? So the plausible explanation for this evolution is the in-spiral of two orbiting masses, M1 and M2, due to gravitational wave emission. So here, you notice they do not say that it's a binary black hole. They are just saying like this evolution of the frequency is representing of two masses. And then they go on and say, to reach an orbital frequency of 75 Hertz, half of the gravitational wave frequency, the object must have been very close and very compact, equal Newtonian point masses orbiting at the frequency would be only approximately 350 kilometers apart. A pair of neutron stars is important, while compact would not have the required mass, while a black hole neutron star binary with the deduced shape mass will have a very large total mass and with this merge at a much lower frequency. This leaves black holes as the only known object compact enough to reach at orbital frequency of 75 Hertz without contact. So they are eliminating binary neutron stars, a binary of black hole star and neutron star, and then they say, well, this is black holes are the only choice that we have. So, however, I think there is still an epistemic concern. Well, without justified constraints on the number of theoretical models, the process may select an incorrect entity, as the correct model might exist outside this considered set. If we compare it with Massimi, well, let's say Massimi's framework may address the selection of the theoretical entities. The concern of an unjustified constraint on models raises the risk of misrepresenting the evidence, a challenge that actually she doesn't touch upon. To support that, going back to Bas van Frassen, you all know that in the scientific image book, he draws a distinction between observables and unobservables based on naked eye. And then in the other writings, he extends the realm of observables to images produced by instruments, but he remains agnostic about, well, the source behind these representations. And I think the best explanation for this move is that the source is underdetermined or not demonstrable. And the evidence for that is his best of bad lot objection to IBE. And I think the objection can also be extended to IOE, since IBE and IOE differ only in the second step. So in IOE, the second step is bidirectional elimination, and IBE is based on explanatory power. And the question is, well, why do scientists commit themselves to using the concept of observation in these cases, despite the problem of undetermination of the source? What could explain that? That's where I believe that meta-empirical assessments can support this claim. So in order for the bidirectional IOE to work, one needs to justify delimiting the number of alternatives in the first step. For that, one needs to justify the basis for taking the background theory or its possible extensions like PPE as theoretical constraints to delimit the number of alternatives one can consider for the source. And if we go back to Stanford, he has already identified this problem in eliminative reasoning, like generally. And there's a paper by Casey McCoy. He suggests to resolve this by invoking meta-empirical assessments developed by David. And I think it's now clear that the bidirectional IOE in the process of observation is a species of general eliminative reasoning, and only specific feature is a bidirectional inference in the source in the second step. So therefore, it's reasonable to extend the treatment suggested by McCoy to justify the inference to the source in the observation of binary black holes via gravitational waves. So the problem can be presented in a kind of dilemma. Well, if one infers binary black holes on the basis of narrowing down the number of alternatives by assuming that GR and its PPE extensions are correct, one must epistemically justify this assumption. Otherwise, if the assumption is pragmatically motivated, the inferential step towards selecting binary black holes as the source of detected gravitational waves is epistemically unfounded. So since the general view tends to reject the second horn of the dilemma, the only possible option, I argue, it is to accept the extension of the concept of evidence beyond the empirical in order to overcome the undetermination. So that means we must provide epistemic reasons for believing that there are no other valid alternatives beyond the considered set of alternatives in the context of the inference to the binary black holes. So the question is, why assume that the source of gravitational waves aligns with basic GR assumptions despite the lack of testing in extreme gravitational regime? And this assumption should be justified by some kind of evidence which goes beyond empirical evidence, in order to because the assumption is based on strong limitations on scientific determination, or in other words, strong limitations on the space of alternatives. And a kind of meta-empirical assessment that could support this assumption is David's three arguments. So you may all agree that there is no viable alternative to GR after extensive search, like James has written about. I think that might be controversial. And GR has a successful history of predictive accuracy within its research program. And in the case of unexpected explanatory argument, GR's explanatory power extends beyond its original scope. So these meta-empirical observations strongly limit the scientific determination, suggesting a high probability that GR's basic assumptions hold true in the extreme gravitational regime, especially in the case of binary black holes. Now, one might argue that, the parameterized post-Einsteinian framework encompasses a wide variety of modified gravity models in the vicinity of GR. That is, those models that are metric theories and are considered viable options to pursue. There's the concern about gravity theories that do not assume a metric framework as their basis, like let alone unconceived alternatives, is not justified since we have a substantial amount of evidence for GR. So any modified gravity theory must remain close to GR assumptions to account for this remarkable success, right? Well, it's the objection actually implicitly, I think, invokes Dawit's meta-inductive argument, and from it argues for a strong limitation on scientific determination. That means the meta-observation that GR has been remarkably successful in is used to confirm the claim that any future theory of gravity should account for the successful history of GR, which in turn also imposes limitations on scientific determination. Otherwise, it is crucial that the empirical evidence for predictions derived from GR in its domain of application cannot support the claim that there is no alternative. So the empirical evidence kind of cannot take care of the problem of unconceived alternatives. Yeah, well, to conclude, I have argued that the philosophical accounts of observation fail to account for the observation of binary black hole merger with regard to inference to the source. This observation indicates that the requirement of an independent theory or independent empirical support is not necessary to infer the source of information. And the logical reasoning that the scientists in practice employ is a bidirectional inference to the only explanation. And for that, we need an extension of the concept of evidence. Thank you very much.
Right, thank you. So we'll take